Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you. So I'm going to talk about our work on reconfigurable network embedded sensor systems, and this is going to be the outline of my talk. I will very briefly give an overview of some of the research activities at ISIS. Then I will go to the second part, which is describe a dynamic software reconfiguration approach we have developed and try to evaluate a little bit the approach with some experimental results we have. And then at the third part of the talk, I'm going to discuss ongoing work and for a service-oriented architecture where we try basically to address some of the limitations of our approach. So at ISIS, there are multiple, we're looking at different research problems, and what I did, I asked Akos Ligdesi to give me some of his slides about some of the recent developments. And this slide describes a new sensor localization algorithm that's going to be presented at Sensis next month. So the basic idea is that two nodes transmit with no frequency separation, and some receivers are able to measure the phase difference between this low change signal, although they use the wavelength of the carrier, which is much faster. And by just using this idea, you can achieve very good localization. So these graphs, and I don't know, my laser doesn't work, but this graph shows experimental results for a 5 by 6 randomized grid. Thank you. Where the ground truth goes around 5 centimeters, and using this algorithm, the mean error for the localization was around 7 centimeters. And around 85% of all the nodes were within 1 lambda, where the lambda is the wavelength of the carrier signal. Of course, in order to do that, the nodes should be synchronized. So this slide describes the time synchronization algorithm that has been developed at ISIS. This is the graph here. It describes the experimental results for a 9 by 9 node in this grid. This purple curve describes the average error, which is around 2 to 3 microseconds. This blue curve describes the maximum error, and the yellow curve describes the percentage of the nodes that are synchronized. And you can see that this converges to probably around 10 seconds. And later on, what we do, we shut down different sensors to try to see how the time synchronization algorithm behaves. And I think this is pretty good results, and both the localization and the synchronization algorithm have been driven by this application, the shooter localization application, where basically the objective is try to localize a shooter in an urban environment using acoustic sensors. This is achieved by looking sensing both the muzzle blast and the shock wave of the shot, and basically using the localization and the time synchronization algorithms, the accuracy, the 3D accuracy of this algorithm that was demonstrated in a marine base was around 1 meter, and the latency was less than 2 seconds. So these are some of the things that are going on at ISIS, but today I'm going to talk about a complementary approach, looking at software reconfiguration. So in the previous two talks, I think it was apparent the need for reconfiguring application sensor networks is obvious, because you like to take into account dynamic functional and performance requirements, and also the uncertainty and variability of the environment. So what we are concerned with here is try to develop adaptive sensor network applications that are able to detect the system changes, can reflect on the event occurrences, and be able to adapt to new operating conditions. So in particular, we're going to look at runtime technologies in order to do that. So what are the basic problems for being able to determine what the configuration of the network is going to be at runtime? So there are different types of reconfiguration that we can think of, and some of them are already implemented. For example, we have ad hoc routing. We have different schemes for saving power. So here we're concerned with a richer form of reconfiguration that we assume that we can change the functionality of individual nodes. We can, of course, switch nodes on or off. And we can, if we want to reroute the data processing flow in a dynamic manner. Now, there are a lot of reconfiguration approaches that have developed for other applications, for example, multimedia networks. But usually, there, the assumption is that you know all the system conditions, you enumerate them before, a priori, and you create a small lookup table, and you switch between these configurations. This is not going to work in sensor networks. Simply, the number of configurations is too large. So we need a way to compute online what is a suitable configuration. And then we need the infrastructure to deploy the configuration. So that's where I'm going to focus today. I'm going to use a very simple example in order to illustrate the approach. This is the hallway at the ECS department at Vanderbilt. And basically, the case study is tracking people working in the hallway using some cameras. I'm going to give the technical details of the sensor network later in the slide. This is not a power or a resource-constrained network, but I think it illustrates what we can do so far. So before that, let's try to formalize a little bit the problem. So I'm going to define the design space of the application as the formal model of all the software components with any alternative implementations if they exist, and also the interactions. And I'm going to call this space operation space when it's embedded to the application. So then the reconfiguration can be defined just as a process from transitioning from one point in this space to another point. Why do we want transition? Because the system requirements have changed, something has changed in the system. So we have to solve basically two problems. We have to find the next point. What is the next point? What is the next configuration? And also we have actually to perform the configuration in the network. Now, in our approach, we are going to describe system requirements using formal constraints on different parameters such as power, latency, accuracy, and other quality of service parameters. And for that, we are going to use OCL, Object Constraint Language. And I'm going to go through some of the examples of the constraints. So this is our problem. And this is the architecture that we have developed. So let me go through the architecture first, and then in the later slides, I'm going to focus on the different components. So basically, this architecture is a simple feedback loop. There are some monitor components in the nodes. This is the bottom part that runs on the nodes that monitor the different operational parameters of interest. They send their data to a base station where there is a global constraint monitor. When some constraints or the system requirements are violated, this is going to invoke the reconfiguration process that is based on a design space exploration tool, which is called desert here. What it's going to do is going to take as input the model of the application. Is going to take the constraints, the current values of the operation parameters. It's going to try to find a feasible configuration. And from that, we're going to generate some configuration files, one for each node. We're going to send them to the network. There's a configurator component on the nodes that is going to stop some applications, start some others, and rewire the applications so continue the network application. So this is the idea of the reconfiguration architecture. So let's try to go a little bit on the different components. And we're going to start with the model. So we have developed this modeling language, a graphical modeling language that captures the design space of the application. We're using a meta-modeling tool called CME that has been developed at ISIS. The idea is to develop the model applications using UML diagrams. And for this application, we need, for every modeling language, of course, we have to define the semantics. For this application, we're using asynchronous data flow for the semantics. And here, what I saw is a simple application graph of the application graph that runs on a component. I have zoomed in on a particular component. And we can see that we have the alternative implementations of the component. And we have some condition objects that describe all the constraints that affect these components. And we can define these constraints, and you can all see that here using OCL statements. So this is the modeling part of the architecture. So the cornerstone is this design space exploration. So how do we do that? Before we do that, we have to formally define our design space. So I'm going to define the design space just as a hierarchical composition of different elements. And we're going to have two operators for the composition, either end decomposition or composition. So whenever we require both components to be part of the space, or decomposition where we can use only one component of a certain type. And we're going to associate with these elements some properties that are going to characterize basically the elements. we have to describe how these properties can propagate in our hierarchy, and for decomposed elements, we're going to take the exclusive OR of the properties. Now, for end decomposed elements, we can define different composition policies. We can assume that the properties are composed additively, multiplicative, take the maximum, minimum, or we can define any custom composition policy that we want. For example, in the example that we do, I'm going to use the additive policy for power. And the next element of the design space representation are the constraints that we like to evaluate our design space over. And for that, we use OCL, and we have to describe some things in more detail about the constraints. We have two different types of constraints. We have compatibility and interspace constraints that describe semantic compatibility between components. For example, we can say component A always requires component B. We represent them symbolically using a Boolean expression over the Boolean representation of the elements of the design space. And we have the second type of constraints, which are property constraints that basically are bounds or inequalities on the different operation parameters, power. Or we can describe, for example, that in order to localize the target, the locations of the nodes must surround the target and so on. And these are derived from structural characteristics of the application. So in order to formalize these constraints, we use OCL. We have different operators, context operator, navigation operators in order to navigate in our hierarchy. We have some property operators in order to describe the different operational parameters like latency, cost, and so on. And then we can use arithmetic relational operators and logical operators for composing more complicated constraints. So this is the design space representation. And this is some example of the constraints. So first of all, the first two examples are compatibility constraints. So we have, for example, that if we choose estimator 1 as an alternative for our estimator, then we have to use data collector 1 and so on. And these are basically just inequalities on the operational parameters. So what we do, as I said, the space is described as a hierarchical composition of elements. So here you can see a picture of that, an AND/OR graph. We need a formal representation of this graph. For that, we use a Boolean representation, and we encode that using OBDDs, ordered binary decision diagrams. And we also encode our constraints using Boolean expressions, assuming that the operational parameters take values in finite domain. And what we do, we apply the constraints over the space, and we compute a feasible configuration. Most of the times, this method is going to compute more than one configurations. If we want to do that in an autonomous way, we need some heuristics. For example, we can take the first configuration that is computed and so on, or we have put some heuristics in order to optimize the configuration. So let me just go back to the case study and describe a little bit the experimental results of this architecture. So this is the testbed, a wireless network with 8 nodes, open brick, 802.11. We use a camera for tracking people. It's not source constrained. We have 256 megabyte RAM, and we use Linux, and we use AODV for routing. So this back the operation was setup of the application. So what we do, one-dimensional tracking of people walking in the hallway. We have different software components, for example, motion detection for initialize the tracking using Kalman filtering, data recording, and communication. We may have multiple people walking, but we are going to assume that there is only one person per field of view in order to simplify a bit the signal processing. And the sampling frequency was set to 4 frames per second. That is fast enough for tracking people walking. So we have designed multiple alternatives of the same configuration. So estimator 1 is a Kalman filter, a standard Kalman filter. Estimator 2 is a Kalman filter plus a prediction model for predicting the motion of the person in the field of view of the neighboring nodes. So the idea is that if one of the nodes shuts down because it doesn't have enough power or fails, then the node that is next to it can use a prediction model in order to predict the motion. And this leads to two different data collector components. So now, even for this small network, if we compute all the different configurations So for each node, we have three configurations. Either the sensor node can operate in one of the two possible configurations I described, or I can turn off one of the nodes to save power. Then we have 6,561 configurations. So we have to compute the configuration online. If we take the functionality constraints, then the configuration is 69, so it's much smaller. And what we do, in this case, we drive the reconfiguration using a parameter vector that indicates the available power on each node, and also a measure of the accuracy of the algorithm that can be, for example, covariance of the Kalman filter. We are going to assume that the power consumption of the second configuration is higher, and also we're going to assume a linear composition model for accuracy. So if we want to increase the accuracy, we have to turn on more sensor nodes. So these are the experimental results. So the track of the people walking the aisle is what we expect to be. So the first curve here, these are shifted in time, so they do not overlap, is with the first configuration. The second is when a node shuts down, and still we're using the first configuration. The third is when the node shuts down by using the predicting model, and we can see we can have some measurements in the gap. The most important thing about the experimental results is try to measure the overhead of the approach. So this summarizes the overhead for 10 experiments with 1, 2, and 3 people walking in the aisle. So we measure the time needed for the time that the base station is going to invoke the configuration until it sends the configuration file to the nodes, and this was about 10 seconds. And also measure the time that each node needs in order to stop some of the application components, start some others, and rewire the components. This was around 8 seconds. So therefore, our total configuration time is approximately 18 seconds. We don't think that this is too bad. On the other hand, we can improve that, and we're looking at different directions. And now I'm going to move a little bit to the ongoing work. So there are multiple challenges that probably we need to address for such an approach. The one is, can we decrease the number for reconfiguration? The problem of this approach is that it uses a global model of the application. So somehow, can we use a localized reconfiguration? Also, what about robustness? Can we formally include some constraints that represent desired redundancy in the application? And if we have resource constraint nodes and we cannot assume that we have alternate software components, can we use alternate sensor nodes in order to do the reconfiguration? So we're working towards these goals. And we have developed a service-oriented architecture trying to address some of these challenges. So the idea here is that instead of using the node as the central notion in the architecture, we use the phenomenon we like to sense. For example, in this case, a human. So we're going to call that a target. We create a target object, which is a representation of the target that drives the application. The target object consists of a finite automaton, and for each state of the automaton, we assume that we know the service graph that describes the processing, what the network should do in order to perform the processing for this mode. Modes can describe things like the object is stationary, is moving, is turning, is running, and so on. And also the object contains some state that we like to sense. And of course, the target object can migrate from one node to the other and can switch between different modes based on sensor information. So the moment we switch from one mode to the other, we have a new service graph, and somehow we have to go and allocate and schedule these services to the available nodes. So the main challenge in this architecture is to design this scheduler allocator. I don't know if we don't have a better name for that yet, but what's the idea here is that this component is a runtime component that takes as input the desired service graph, a formal model of computation of the service graph, and it's trying to find what are the available services in the tasks so that it can deploy this service graph. So basically, it has to solve both a scheduling and allocation problem. And we assume that it can use different middleware services that are available, for example, a distributed discovery service, a binding service, routing, time sync, and so on. So let me focus a little bit on these components, so how we are doing that. So as I said, the main disadvantage of the approach was that it was using a global model of the system. So instead of having a global model, we assume that the node with the target object is querying the neighboring nodes and is create a local object at runtime. So after we do that, allocation of tasks and scheduling can be solved using the constraint satisfaction problem approach that I described. Because we have a local model of the system, we have the service graph that represents the constraints. So if we solve this local constraint satisfaction problem, we can allocate the services to nodes and also schedule the services. Here it's interesting that we have another stage of scheduling at the lower level. The moment we have decided which services are going to run at each node, somehow we have to go and schedule these services at the nodes. And there are some interesting theoretical questions, so it's not obvious that we can compose these schedulers, or it's not obvious we can have any properties about guarantees about this scheduling. So that's what we're working on. And this figure shows we're using a model-based approach in order to design the scheduler allocator, and this shows some of our initial efforts. And the driver for this work is a distributed gesture recognition approach in collaboration with Professor Wayne Wolf at Princeton. And we have already developed a little bit the model of the application. So in this case, this is the finite state machine of the target object. It has modes like the human is in the overlap of two different field of views or is out of range and so on. And for each mode, there is a service graph with services like read frame, segmentation, contour following, ellipse finding, and so on. Since there is a lot of legacy code here, we decided to use J2EE for the service part. So we wrap all this code in J2EE code and provides a lot of the things that we need, like transport protocol, all the XML stuff, and also provides a distributed discovery service. So this is ongoing work. Hopefully we're going to have some results soon. And I think this summarizes what I wanted to say. Basically describe our dynamic software configuration approach, describe its limitations, and our current work trying to address some of these limitations. And I would like to thank also my collaborators, Sandeep and Janos, and some of the students that have worked on this project. Thank you. So, for example, in the distributed gesture recognition approach, there are different services that have to run depending on the mode of the target. If it's in the overlap of the field of view, there is viewed by two cameras and so on. So in this case, the service graph is going to be completely different. So another example is that if we have some application and we do not require necessarily that all the services are at each node, but different nodes provide different services, different sensing modalities, and so on, and we choose the sensing modality on the fly, and so on. Did I answer your question?
Well, I have a follow-up question that kind of gets at the same thing. So I think there's a question here about what programming model does this imply? What you're proposing to do, as I understand it, is to construct these configurations of software components on the fly based on some expressive statement of the resource requirements of each one, of the interactions between the different components, of the suitability of different components in different environments, of the resource constraints of the application. And I find it hard enough already to ensure that my time sync protocol and my routing protocol are going to work together. And you have used, your FTSP, for example, so we have experience with some of that. And the question is, do you really think that what we're going to end up with is a way of optimizing sensor networks by having this plethora of potential software components that we can plug together on the fly, and then as the network is operating, reconfigure the software and reprogram the nodes so that they're suddenly using a new set of services as they're running? It sounds to me like if we wanted to get towards more reliability and robustness, that's kind of the opposite direction that we want to go in. I think optimization is really important, but why not focus more on a parameter-based approach? Don't change the software. I would never want to change the software if the network is running. That's sure that's going to kill you because it's going to crash or you're going to have a bug or something. Get the hardened software, but then
So, I mean, changing the parameters, first of all, we can address that with this approach. It's much more powerful since we have this space representation. So we can go and change some approach, some parameters of the different components and have a similar feedback loop that we're trying to optimize these parameters. Correct?
Okay, but it sounds like that would, I would focus on that one.
So this is a little simpler problem. So I understand that it's extremely useful as well. But I can think of cases that, and some of the tracking applications using cameras are some of these cases that we have to change the software components no matter what.
I guess I don't see that, and I need to know more about that aspect.
So, for example, when we do the gesture recognition, depending on where the human is, if it's viewed by multiple cameras, then, for example, if you want to identify its hand by an ellipse, then you have to see one part of the ellipse can be in one node, and one part of the ellipse should be in the other. And in this case, the software that does the collaboration should be completely different than the case the human is in the field of view of a single camera. So how do you switch from this configuration to the configuration and overlap? I mean, what do you do?
It's very complicated.
One area I wonder if this could be really helpful would be to recover from failure, where you actually suddenly have a node which you get your component out of the network, which then you have to actually decide where to move that.
That's I think a better example.
I think on that thing, you have to move a known software configuration, not dynamic on slide to slide, which the software will put together, but now they put together to work out.
And then there's overheads associated with changing your software configuration and maintaining state in these components and how does the state get transferred and what kind of warm up. You know, when you start up FTSP, it can take minutes or hours to actually synchronize. And so if I swap my time sync protocol out, then I suddenly lose sync. So there's all kinds of other constraints, I think, associated with the reconfiguration.
In the industrial monitoring space, I mean, very often we run into issues, for example, that people want additional functionality. So this may be a way to add functionality to something that exists. Maybe even replace components with newer versions.
Yeah.
And that, I mean, usually you don't want to bring your whole monitoring network down because it has to run 24/7, you know, in order to do that. So I think that's an methodology.
Yeah, so I think applying this in an evolution to the evolution of the software makes a lot of sense. Like, I guess I'm more nervous about the idea of the network changing the software on the fly without human interaction. I'd like that to be part of the software evolution.
Thank you.